Bismillahirrahmanirrahim. This is John Gidpada Sumru, Assistant Professor, Electrical Engineering Department, Saqqara University, Pakistan. In our first part of video, we discussed on this review article a detailed review of MMC circuit topology and modeling issues. We discussed about the abstract in the first part. In this second part, we will discuss about introduction. Over the years, there have always been heated disputes between the supporters of DC and AC systems. In the 1880s, electricity development experienced major inventions, and the war of current between Nikola Tesla and Thomas Edison started, which lasted several years. Yes, it is true that there was a very hard debate whether to select DC systems or to select AC systems, which systems have more advantages. So this debate remained for several years. The earliest electrical system was introduced by Thomas Edison in 1882. His electrical system had DC generators driven by steam engines to supply direct current DC at 110 volts. However, in the late 19th century, the war ended as AC won, and there had been a decline in DC systems. Yes, at the initial stage, AC dominated over the DC due to the inventions of induction motor and AC transformers. So, breakthrough at that time was the invention of AC transformer. AC transformers facilitated cost-effective transmission, and thus HVAC was considered the most economical choice for decades. But again, has re-emerged and has been preferred over AC after the rapid advancement in the field of power electronic devices and power converters. After the invention of IGBTs and other power semiconductor devices, the DC systems again uh, re-emerged. The DC system rebooting started in 1954 when ABB accomplished the high voltage direct current HVDC project between Gotland and Swedish Mandel. Most countries worldwide have set an ambition to increase renewable energy resources to meet energy targets and combat climate change while increasing energy security. Yeah, this is true. The world is moving towards renewable energy sources such as wind, solar, and others. European Union has set a target for the year of 2050 to reduce 80 to 95% of greenhouse gas emissions compared to 1990 levels. In this regard, European Wind Initiative has decided to replace 50% of non-renewable power sources with wind power generations. Since most renewable resources, such as offshore wind farms, are suited at remote locations, the requirements for long-distance power transmission and asynchronous interconnections are increasing. Yeah, long-distance power transmission requirements are increasing. Asynchronous. What does asynchronous interconnection means? Asynchronous interconnection means when different systems with different frequency ratings and voltage ratings are integrated, then this is called asynchronous interconnection. In HVAC, asynchronous interconnections are not possible, but in HVDC, asynchronous interconnections are possible. This is one of the main reasons HVDC is preferred over HVAC. HVDC is a well-proven technology to meet these requirements and is a promising technology for future power systems. True, MMC HVDC for an offshore wind farm is shown in figure 1. This is a wind farm. Now this wind farm is feeding to this AC grid. All right. HVDC can be used for asynchronous interconnection such as technical mismatch system with different grid frequencies and voltage ratings can be interconnected. This is one of the significant advantages of HVDC as compared to HVAC. HVDC is preferred over HVAC in applications such as underwater long distance cable crossing, bulk power long distance transmission, and underground long distance cables. So these are some applications where HVDC is preferred over HVAC. All right. Now basically there are three power converter topologies. that have been used historically for HVDC project. One is the LCC, land commutated converters, also known as current source converters. Another is the VAC, voltage source converters. And currently MMC is dominating the HVDC technology. And MMC, let me be very clear that MMC is advanced variant, latest generation of VAC. In 1940s, only LCC was used commercially. Before the 1970s, mercury arc valve was used in LCC, but after the 1970s, thyristor technology was introduced in LCC. LCC-based HVDC system dominate the long distance and bulk power transmission. Many LCC-based HVDC projects have been installed and few are under construction. The project that is currently installed in Pakistan from Bhatia to Lahore is also LCC-based project. LCC have relatively high line impedance and thus have the natural ability to slow down the rise of DC fault current, making AC circuit breakers suitable to low protection. Yes, this is a clear advantage of LCC, that they have relatively high impedance and therefore natural ability to slow down the rise of DC fault current in case of DC short circuit or any other fault. So due to the slow rise of the fault current, it gives the time for the AC circuit breaker to open and give the and allow the protection. So this is the advantage. But in case of MMC, rise of DC fault current is very fast. So AC circuit breakers in some applications over there are not suitable because they are slow and the system overall can damage, and therefore in those systems we prefer DC circuit breakers, and a lot of research is ongoing on the DC circuit breakers. This current feature is missing in MMC with half-bridge topology and VAC. Yeah, in case of VAC and MMC, this feature is missing. Therefore, DC fault becomes a critical issue. True. DC fault is a very critical issue. Arm inductors in MMC and transformer leakage inductors in VAC mainly limit the DC fault current. Moreover, DC circuit breakers, advanced extruded DC cables, fault blocking submodules, MMC topologies with fault ride-through capability, fault current limiting devices, and MMC controls may be used to address critical DC faults in VAC, MMC. True. These are different ways to overcome this DC short circuit fault condition, DC pole to pole short circuit condition. All right. Now, sometimes DC fault, pole to pole short circuit fault, can be cleared, or fault right through capability can be possible by converter blocking. Converter itself blocks the fault. It is also possible that this fault can be blocked by hybrid circuit breaker blocking. I mean, your circuit breaker, your DC circuit breaker blocks this DC fault, and if it is for a temporary time period, then it restores the systems to its original settings. All right. So DC fault right through is itself a very hard research topic going on in the research area of MMC HVDC. Another drawback of VAC MMC HVDC lower current and voltage rating compared to LCC. Yeah, but in the last decade, these ratings have increased significantly. Previously, LCC had higher efficiency than VAC MMC, but with developing power electronic devices, MMC is arriving at efficiency closer to LCC converter. However, LCC technology is not preferred for future power system due to several limitations such as need for fast communication, complex control system, use of semiconductor devices that cannot be turned off autonomously because ACRs are used. ACRs are not fully controlled devices, they are semi-controlled devices. They can be turned on automatically, but they cannot be turned off automatically. Operating in lagging power factor, limited reactive power control, and inability to use in the isolated system. Moreover, in the LCC, independent active and reactive power flow is not possible, but in case of VAC and MMC, independent control of active and reactive power is possible. Another major limitation of LCC HVDC is inability to change the direction of current, that it needs to reverse the voltage polarity to change the power flow direction. Yes, because ACR is a unidirectional device, silicon control rectifier is a unidirectional device, it allows current in only one direction, but in VAC and MMC, IGBTs are used, Comparatively, IGBT is a fully controlled device and it allows current in bidirectional way. So without reversing the voltage polarity, power flow direction can be changed in case of VSC, but it's not possible in LCC. LCC can conduct current in only one direction while blocking voltage in both polarities. Moreover, the LCD type converter has short circuit ratio of more than 2, which means that it cannot be adequately interfaced with weak AC networks such as offshore wind power plants. Yeah, this is true. Offshore wind power plants cannot be integrated in an LCC, but weak grids such as offshore power plant can be integrated in VSC based or MMC based converter stations. The real breakthrough came with the invention of IGBTs in 1997, making VSC MMC HVDC technology superior to LCD technology. The use of VSC MMC as compared to LCC offers the following advantages. Yeah, these are the advantages of voltage source converter and MMC technology. It can eliminate commutation failure due to the disturbance in AC network. It offers flexible and independent control of current converters, active, reactive power consumed or generated. Yeah, let we mostly use synchronous reference frame theory or vector control current principle, and in that principle it is very possible that you can control the active power by controlling the D component of current, which is real quantity, and reactive power can be controlled by controlling the Q component of the current, which is imaginary quantity. So independent active and reactive power is possible. It can operate with delay and advanced power factor, and it is possible to sync and source reactive power in case of VSC MMC. It is possible to connect VKC networks such as offshore wind power plants, TAD, improved TAD, lower TAD is possible, improved power quality is possible. In case of MMC, the size of filter is reduced, or sometimes no filter is required. In most of the cases, even no filter is required in case of MMC. It offers black start capability. If the system is getting tripped due to some reason, then without any external power supply, the system itself can restart. This is called black start capability, and there is no need of a transformer to assist the commutation process. The dynamic behavior allows AC fault right through capability. Yeah, this is very important feature. AC fault right through capability means if there comes any symmetrical or asymmetrical AC faults such as line to ground fault or three phase to ground faults, or any other fault is coming, whether on the grid side or whether on the load side in the MMC based HVD system, the system must survive itself and must restore to its reference values. After the fault is cleared, the system should restart and system should continue its working and operation. This is called AC fault right through capability, and this itself is a very hard research topic in MMC based HVDC area. It requires less space and has less footprint and weight of the converter than LCC. Therefore, offshore wind power plants which need a DC cable connection prefer VSC MMC technology. It can change convert current in power flow direction without reversing the polarity. Power switches in VSC MMC has bidirectional current carrying capability. Therefore, VSC MMC technology is ideal for implementing multi-terminal direct current MTDC power kits. So, in case of MTDC applications, VSC MMC are preferred. DC power cables are lighter in weight, and we have lower installation cost in MMC VSC. VSC MMC use fully controlled power semiconductor devices that can be autonomously turned on and off. After this, in the third part of video, we will continue the discussion. Thank you very much.